previous cases we had obtained f of s as the Laplace transform for a given f of t. Now if it's the other way round, that we have f of s as the given function of s and we wish to obtain f of t, then it's pretty obvious that we'll be performing an inverse of the Laplace transform, which is what we are to study in this video. So the Laplace transform has just gone to the other side and we have the inverse Laplace transform operator. A few of the formulas that are associated with the inverse Laplace transform have been given as follows. So here are some of the important formulas that you can come across, and these will be useful in obtaining the values that we are to carry out the numerical problems that we will be doing, and you can actually prove them. And if you look at them, you will find that it is exactly the other way around. If you remember the Laplace transform, like in case of the very first case, you can see that the Laplace transform in that case of 1 was 1 over s, so the inverse is going to be just the other way around. And same goes with the trigonometric functions, the exponential terms and the hyperbolic as well as the normal trigonometric functions. So all of that you have studied in Laplace transform has been provided the other way in this case, that is the inverse Laplace transform. We can try a few examples so that we get acquainted with all these transforms, or at least the useful ones, the ones that come up regularly. So let's see if we have the case of the inverse Laplace transform of let us have 1 over s squared minus 9. And as you know that 9 is obviously 3 squared, so what we can do is we can multiply a 1 over 3 such that we get a 3 over here, and we have s squared minus 3 squared, that is for 9. And this is of the form as you may come across over here, that is s over s squared minus a squared, which is this one. Where is it? Probably this one, yes. But that's not actually s, but that's a. Now if you look at so that won't be the formula that we were talking about. That will be 1 over a sine hyperbolic 80 that you can see just below that, so that a can, being a constant, that can cross multiply onto the other side. So we have the Laplace inverse of a over s squared minus a squared to be equal to sine hyperbolic 80. So that is exactly what we will be getting here. So this is 1 over 3 remains as such, and this one is simply sine hyperbolic 3t. Instead of a, we have the value 3 over there, so this is simply sine 1 over 3 sine hyperbolic 3t. Next we can take up the case of the Laplace inverse. So this was the first one that we attempted. Let us choose the Laplace to obtain the Laplace inverse transform of 1 over 2s minus 7. Now in that you can take away that 1 over 2 and you have the Laplace inverse of 1 over, since 2 has been taken as the common one, so s minus 7 over 2 is what we are left with, and s minus a gives e raised to the power at that we have obtained over here. So this is simply half of e raised to the power, that is the exponential of a. Instead of a we have 7 over 2 times of t in this case. So that's 7 over 2 times of t. I can try one over here at the top right hand side, vacant space. That is, let's say we have to obtain the Laplace transform of, let's take a more complicated one, that is the Laplace inverse of s plus 2 divided by s plus 2 squared, although it looks complicated, it's not, as you know it, and this is 25. Now that's nothing but 25 is simply 5 squared, and we have s plus a, but in the formulas that we have considered, we have s minus a, so we can take the a as the negative case over here. So minus 2, we can take a as minus 2, so that will be minus of minus 2, which will give us s plus 2. So this one simply becomes Laplace inverse of s minus of minus 2 over s minus of minus 2 squared minus 5 squared. And where do we get a formula? Well, if you look at this one, that is over here, so you have e raised to the power at, and then you have the cosine hyperbolic uh, bt, b being that 5 that we have, the square term. So this is simply e raised to the power at, a here is minus 2, so e raised to the power minus 2t, and then we have the cosine hyperbolic, b is 5 over here, so this is 5 times of t. So that's the answer that we were looking for. Now let's try this Laplace inverse transformation, where we are having s squared plus s plus 2 over s raised to the power 3 over 2. Now that is simply, well, we can operate that, we can divide that s 3 over 2 in each of those terms. What we end up with is that we have an s raised to the power half for the first term, followed by the Laplace inverse transform of s raised to the power minus half for the second term, and for the third term we have the Laplace inverse of 2 s raised to the power minus 3 over 2. And as we know that the Laplace transform of s raised to the power n is going to be equal to the formula that we have at hand, that is t raised to the power n minus 1. So this is t raised to the power n minus 1, here is t raised to the power half minus 1 is going to be minus half, divided by n minus 1 factorial, so this is minus half factorial, then plus over this, in this case t, this is raised to the power minus half minus 1 is minus 3 by 2, and this is minus 3 by 2 factorial, and then finally for the third term we have minus 3 by 2, we have a 2 outside, and then we have t raised to the power minus 3 by 2 minus 1 is minus 5 over 2, and minus 5 over 2 factorial. Well, a small correction over there, because even I felt that that's not coming right, because we have 1 over s raised to the power n, and the Laplace inverse transform of it is going to give us t raised to the power n minus 1 divided by n minus 1 factorial. So n in the first case is going to be well, in the first case it's going to be minus half, because we have s raised to the power half, so when it is taken in the denominator we'll have minus half. So minus half minus 1 is going to be minus 3 over 2 instead of minus whatever was written, and then we have a minus 3 over 2 over here as well, the factorial of it. And when we have s raised to the power minus half over here, that means it's already in the denominator, that is s raised to the power half. So half minus 1, that is n minus 1 for the power term, is going to give us minus half, so minus 1 over 2, and also minus 1 over 2 in this case. And as for the last one, we have 3 over 2 in the denominator, the power of s, so we'll have 3 over 2 minus 1, that will give us 1 over 2 and 1 over 2 in the denominator, the factorial of it as well. All of that will give us, we can interpret them in gamma function. That is, the first one over here is t raised to the power minus 3 over 2. We'll be learning about gamma functions in the other videos. So this minus 3 over 2 factorial is simply equal to gamma minus half, and for this one we have t raised to the power minus 1 over 2, and this is gamma half, and then the final one, that is 2, and that is going to be gamma 3 over 2 times of t raised to the power 1 over 2, and in the denominator we have gamma 3 over 2. Now all of these have values. T raised to the power minus 3 over 2 remains as such. For gamma minus half, we have the value to be equal to minus 2 root pi, and for this we have t raised to the power minus half. This is simply root pi, and for the third term, that is 2 times of t raised to the power half, this is half gamma half, which is half times of root pi. So root pi remains over here, the half term gets multiplied at the top, so we have 4 times of t raised to the power half divided by root pi. So we can take all those root pi terms as the common denominator, and so we have 1 over root pi, and this one's we can take the 2 as the LCM as well, so we can take the 2 over here. For the first term we have a negative sign, so this is minus t raised to the power minus 3 over 2. Then we have 2 times of t raised to the power minus half, and then we have 8 times of t raised to the power half. So this is what we get in by the Laplace transform of this thing that we discussed, the inverse Laplace transform of what was given. Next we move over to the first shifting theorem in this case, that is, if we have the Laplace inverse Laplace transform of f of s to give us f of t, then the inverse Laplace transform of f of s plus a is going to be equal to e raised to the power minus at inverse Laplace transform of f of s, which is obviously f of t. As for the second shifting property, or second shifting theorem in this case, is the Laplace inverse of the exponential of negative of at multiplied to the transformed function fs is equal to the function of t minus a times the unit function of t minus a. Now we'll be doing a few problems on these theorems or the shifting properties in the next video, and also we'll be continuing with the inverse Laplace transform of derivatives and integrals as well, and a few problems related to them. If possible, we'll try and proceed much deep into the topic later on in the upcoming videos. Till then, thank you for watching.